Sold. All right. The primary text, again, is this Abbott text, but the real text is going to be the game. So let's go to the game. This is the official version. Do I want to work off of the official version or the local version that I'm running now? Let's work on the local version. The official version is basically identical. The local version, I can change things in real time if we realize that there are mistakes. I can also take notes. Here's my ansatz, my hypothesis. My hypothesis is that it's possible to learn this stuff from playing a video game. And until very recently, it would have been extraordinarily difficult to set up such a video game. And now it's easy enough that an idiot like me can try to do it at least. So my hope is that by the end of this course, this will look like, you know, lecture one problem set 1, lecture 2 problem set 2, lecture 3 problem set 3, and so on. And anyone who goes through this entire video game and wins the, you know, kills the big boss at the end, really knows their real analysis. Okay, so let's play. This is Real Analysis, the game. This course is currently being developed. If you see any mistakes, extra points. If you find a mistake or something that can be improved upon, you send a PR. We'll have a session on this, what a PR is, how to use GitHub in case somebody actually wants to do it. This course takes you through an introduction to the real numbers, rigorous epsilon delta calculus, basic point set topology, the kinds of things that happen in an intro real analysis class. So let's go to level 1, the story of real analysis. So you have these 3 sliders. There's sort of a discussion here. There's stuff that happens here, and then there's tactics and definitions and theorems there. And you may want to pull the leftmost slider all the way to the right because we're not going to use these things at the moment. So what follows is just a discussion between Socrates and Simplicio. I'll call him Simplicio, which hopefully explains what we're trying to do here. Can you guys see in the back, or should I make it a little bigger? This is good? The Brandons are good, Sam, you're good? All right. Simplicio says, what is real analysis? Socrates replies, oh, it's just calculus, but done right. Why does calculus need a new name? What's wrong with calculus? What's the matter? Well, nothing really. Quick, what's a derivative? So guys, what's a derivative? I should see 17 hands in the air. Yes. Don't tell me. Sadek.
My question to you would be, are you asking about an operator or function, or what are you specifically asking?
Very good. I'm asking something very naive, just in lay terms, in the sense that you learned in BC Calc or something. What's a derivative?
It's a tool that we use to measure the slope of a function.
The slope. Beautiful. That's all I wanted. Derivative means slope, right? So how do you figure out a slope? Tell me your name.
Oh, Ken.
Great.
I said
Oh, okay. Okay, great. Thanks. Just ready. So what's a derivative? Okay, so Simplicio replies, that's easy. If you have a function f that takes real numbers, returns real numbers, and it's differentiable at x, then the derivative is, you guys all know this formula, f of x plus h minus f of x divided by h. Limit as h goes to 0, that's f prime of x. All right, this is all familiar to everybody. This represents the instantaneous slope of the graph of the function y equals f of x at the point x comma y, but y is f of x. Okay, everybody remembers what a derivative is. Socrates says, very good. And tell me, please, what's an integral? What's an integral? Other than Daniel, other than Sean, Ken. Area under a curve, exactly. Area under a curve. That's easy too. If you want to integrate a function f along some interval from a to b, you pretend that you have infinitely many, infinitely small rectangles. You work out all their areas. It's base times height. You add them up. The bases are all, let's say you have a range from a to b, so that, and we're going to chop it into n rectangles. So the bases are all b minus a over n. This is familiar. The heights are whatever the value of the function is at a plus that many shifts by b minus a over n. And then you sum those, and then you make the chopping finer and finer, and you get the area. Okay, that's an integral. Socrates says, great. And what are the 2 fundamental theorems of calculus? Who can tell me the 2 fundamental theorems? Other than Daniel, other than, I'm going to get it, other than Sean, other than Ken. Don't tell me. Joseph.
One, derivative equals are opposite. So, two, you can solve a definite integral by finding the antiderivative and then subtracting that value at the upper bound minus the lower bound.
Beautiful. Derivatives and integrals are inverses of each other, and integrals and derivatives are inverses of each other. Those are the two fundamental theorems. Exactly right. Exactly right. Simplicio says these questions are too easy. The first one says that if you make a function by integrating f up to some variable amount x, so you make a capital F, which is an integral from a to x of some little f of t dt, then the derivative of that new function is just the original function at x. Okay, so it's like the slope of the function that computes area is the value at that endpoint. That's the first. And the second, the other way around, conversely, if f is an antiderivative, big F is an antiderivative of little f, that is, big F prime is little f, then it's easy to work out the area under the curve because the area, the integral from a to b f of x dx is big F of b minus big F of a. So differentiation and integration are inverse operations. Tell me your name, please.
Y-U-A-N-G.
Okay. Got it. And you say Yuan?
You might go by the university doctor.
Roger. Got it. Thank you. Okay. Everybody's good with the first and second. You remember these things. If you don't know these things, we're in trouble. These things are familiar to you. The first and second fundamental theorems of calculus. Socrates says, perfect. Now here's the problem. Where's the problem? You said words like limit. You said words like where these rectangles are going to be infinitely small and there's going to be infinitely many of them. What do you actually mean by these things? And Simplicio says, oh, you know, it's when something happens eventually, like you just go on forever and whatever happens, happens. You just get used to the feel of it, right? This is how you've done calculus. Yeah, you just go with it, right? You get an intuition for it and you do it. Socrates says, okay, well, I see. I agree that is an okay way of thinking about it for a while at least. And it's in fact one that suited Newton. Actually, Newton was uncomfortable with these things. If you read what Newton says about them, he did it, but he was like, you know, really unhappy with the state of things. Leibniz, who co-invented or stole from Newton, depending on whether you're German or British, Leibniz was a bit more carefree about things. Leibniz went on to, so this is Newton, that's Leibniz. Leibniz taught the Bernoulli brothers. These are the world's first AP Calc students. And they taught Leonhard Euler. They taught Marquis de L'Hopital, if you've heard of L'Hopital's rule. And Euler is really the first calc native, just like you guys are the first like cell phone natives and generally, you know, social media natives. Like you've never lived in a world that doesn't have these things, as opposed to someone who, you know, picks up this technology later in life. Euler is the first calc native, and he just sprouts mathematics. There's no one like him. He's here on the end. That's Euler, and he teaches the rest of us. And by the way, so the two inventors of calculus, Newton and Leibniz, if you don't count people like Eudoxus and Archimedes, the ancient Greeks, the 14th century Indian Madhava, many other people, this is not a history course. Okay, so we're going to throw around a little bit of history just because I have to say it. Otherwise, I don't feel right about it. But I'm not quizzing you on what happened in the 19th century or 3rd century BC. Okay, so Euler, the way all of our modern notation, if you read any Euler, it looks just like modern mathematics. If you go a little bit before Euler, it's kind of clunky and weird. Euler was so prolific that everyone learned mathematics from Euler. And so we write using Euler's notation, which goes back to Leibniz. That's why you didn't take AP fluxions. Newton called calculus the theory of fluxions, you know, small fluctuations, and because he's thinking about motion. Anyway, Leibniz, the term calculus comes from a paper of Leibniz. Anyway, everything was going well, was going just like BC Calc was going until you get to the 19th century. And Simplicio says, what happened in the 19th century? And Socrates says, well, you see, there was a guy named Cauchy. This guy Cauchy comes along around 1810s, if you want to be precise, and starts making a fuss that we're not really doing mathematics rigorously. And he starts to prove the theorems of calculus using something approximating precise definitions instead of just hand waving and saying, I know it when I see it, kind of thing. He's making really good progress, and in particular, he proves a statement. Let me isolate one statement that he proves. If you have a bunch of continuous functions and you take their limit, the limiting function is also continuous. Makes perfect sense, right? What's there to argue about that? Continuity is something, a limit is something where you're getting closer and closer. Continuity is that you can draw something without picking your hand up off the page, no problem. Of course, there's a problem. That's why we're talking about this. Simplicio says, yeah, sure, that sounds perfectly reasonable. A limit is a continuous process. You do that to a continuous function, and in the end, you get something continuous. What's the problem? The problem, Socrates says, well, around that same time, there was another guy named Fourier. And Fourier says that he can decompose an arbitrary function into sines and cosines. This is harmonic analysis, modern harmonic analysis. This is why your cell phones work. And I'll get any function I want. For example, like a discontinuous sawtooth function. Simplicio says, what? And Socrates says, look for yourself. Here's a graph of sine of nx times 1 over n, summed as n goes from 1 to 100. So that's the blue one. If I just take one term, if I just take sine, so sine is this black curve. And if I take two of these, so this is sine of x plus a half sine of 2x. That's the red curve. And if I take 3 of them, that's the green curve, and it gets a little funky. And if I take 10 of them, if I take 100 of them, I get this blue curve. And you see hopefully you see, if you take 100 out to infinity, what Fourier claims is that this is going to become a function that goes straight down and then jumps and goes straight down and jumps. They're all continuous. All of these functions are continuous because sine is continuous for adding finitely many things, but at infinity, you develop a discontinuity. That's what Fourier says. That's the problem. Who's right? So Simplicio says, whoa, wait. I can think of an even easier example. Just look at the polynomials, x to the n, on the unit interval, 0, 1, right? You have the straight line. Let's see, do I have a picture? No. I should add a picture. Where are my notes on the game? Add picture for x to the n. Yeah. You look at x to the n on the unit interval. So y equals x looks like this. Can I do this? Ha! This is cool. You don't see anything yet. So here's y equals x, right? So here's 0 and 1. That's y equals x. Y equals x squared looks like that. Y equals x cubed looks like that. Y equals x to the 4th looks like that. And y equals x to the 100 looks like that. And what's happening is when you take very high powers of any point strictly less than 1, as long as I'm strictly less than 1, and you take a large power, that goes to 0. But 1 itself will always stay at 1. So you don't need Fourier analysis to know that there's a problem. There's a problem already in stupid polynomials on the unit interval, 0, 1. Okay, these are very, very continuous functions. X to the n is as continuous as it gets. And in the limit, you get 0, 0, 0 jumps to 1. So whatever Cauchy said, it's just wrong. Why would he say it? Why was he using rigorous mathematics to say something that ended up being wrong? How did that happen? Okay. So get rid of this picture. So the limiting function is discontinuous. What is going on? Socrates says, very good, Simplicio. Exactly right. Between Fourier and Cauchy, they broke math. You break it, you buy it. We got to fix it. Simplicio says, okay, so what's the right answer? How do you do calculus reason? Socrates says, not so fast. Things got even worse. And by the mid-19th century, we realized we don't even know what the real numbers are. The hell are you talking about? What do you mean? What do you mean you don't know what the real numbers are? Here they are. Here's the real number line. There's 0, there's 1, there's root 2, there's 5/3. We got fractions, we got negatives, we got whole numbers. We even have crazy numbers like I and E. Where's the problem? Socrates says, you guys know something called the intermediate value theorem? What's the intermediate value theorem? What's it say? Other than Daniel. Other than, I'm going to get it. Safek. Other than Safek. Okay. Tell me again.
Uh,
Akil.
okay, be wrong. It's like you have a continuous function, and you have like 2 points on a function, and like there's a value for like everything in between.
Exactly right. Exactly right. The simplest way of saying is if you have a continuous function at somewhere it's negative and somewhere it's positive, then somewhere in between it's got to hit zero. Right? There's no way to be continuous and go from below zero to above zero without hitting zero. Makes complete sense. What's the problem? Do you remember the intermediate value theorem? Simplicio says, sure, you have a continuous function. It goes from being negative to positive, then it has to cross zero somewhere in between. Socrates says, okay, very good. Tell me about the function that takes x, that maps x to x squared minus 2. Are you guys all familiar with this notation? A different way of writing functions. So when we write, we say f maps x to x squared minus 2. When we write f goes from r to r, that means that the inputs are real numbers and the outputs are real numbers, but we haven't actually specified what the function does on those inputs and outputs. So this says that f takes real numbers to real numbers, but if you replace this arrow with one with a tail, so this one has a tail, that arrow has a tail, this arrow does not have a tail. That's if we want to say what happens to a particular input x under the action of f. So any number x gets sent to x squared minus 2. It's the same thing as writing y equals x squared minus 2. Okay. Let me remind you here that x is a dummy variable, so this is the same function as f maps u to u squared minus 2. All that matters is what it's actually doing. Okay, so what happens to this f, this particular f, x squared minus 2? So x squared minus 2, y equals x squared minus 2 is just a stupid parabola. What happens to it on the rational numbers? Simplicio says, okay, if x is a rational number, then so is x squared, and so is x squared minus 2. Okay, so it maps, so we can actually say that f maps rational numbers to rational numbers. Are you familiar with Q, bold Q for the rational numbers, bold R for the real numbers? Over the reals, the graph of y equals f of x is just a parabola, but you asked me about the intermediate value theorem. Okay, so what's the value of this thing at x equals 0? Minus 2. 0 squared minus 2 is minus 2. Okay, and what about when x is equal to 2? 2 squared minus 2. 2 squared is 4, minus 2 is 2, and 2 is positive. So at 0, it's negative. At 2, it's positive. When x equals 0, the value of the function is negative. When x is equal to 2, the value of the function is positive. Go on. Okay, so there's a root of f somewhere between 0 and 2. That's what the intermediate value theorem says. But where does this function x squared minus 2 cross 0? You solve for x. Root 2. The function crosses at x equals root 2, 1.414, whatever. And what did the Pythagoreans know about this number? One of them, supposedly Hippasus, figured out that root 2 is irrational. We'll go over the proof of that later. And that ruined the Pythagoreans' entire theory of geometry and form. They originally believed that all numbers were rational. They had a whole music theory based on it. Legend has it they were so pissed off at Hippasus they threw him in the river for his heresy. And Simplicio says, okay, wait, so if we restrict to rational inputs, the parabola starts out being negative, it winds up being positive, and it never hits 0 in between. Because the place where it hits 0 is not a rational number. If we restrict the inputs just to but rational numbers are everywhere. So what's the difference? What makes the real numbers different from the rational numbers so that the intermediate value theorem actually holds? We don't even know what the real numbers are. That's how bad things got by the middle of the 19th century. Okay, so we have to figure out how to do limits, how to do, what limits mean, what happens to limits and functions. We have to figure out what the real numbers are. That's why we're doing this. There was nothing wrong with the calculus that you learned, except that everything about it was wrong. And we have to start over from scratch and build everything back up. The theorems will be familiar, but the mechanism by which we prove those theorems is what I think will be new. Now, you've had Math 300, or you've placed out of Math 300, because that's where you start learning how to prove theorems. But you'll see, we'll relearn how to prove theorems even more so. All right, let's get started. You guys ready to start the actual course? Now that was the preamble. Okay. So in this course, we will be using technology. This technology is a type of proof assistant. The one we're using is called Lean. Doesn't matter what it's called. It's software that checks mechanically that proofs prove exactly what they claim to prove. I don't get to hide anything under any rugs, and neither do you. Everything's going to be out in the open. It has other very cool pedagogical features that we'll get to later. It'll take a little time to get used to the syntax. So until we're comfortable with the syntax, we'll intersperse teaching exercises on how to use Lean with exercises in real analysis. And pretty soon, all of the exercises will just be about real analysis. Okay, but of course, we have to get started with the basics. All right, here's your first exercise. We have a hypothesis. So our object is a real number x. Our assumption is a hypothesis that has a name. The name of this hypothesis is h. And the meaning of the hypothesis is that x is equal to 5. And our goal is to prove that x is equal to 5. This shouldn't be very difficult. Okay. The fact that we called this h or this x for that matter is completely arbitrary. We could have called them Alice or Bob, or x equal 5 is a good name for a hypothesis, because then you don't have to think about what the hypothesis actually. Once you have 20 hypotheses and you're trying to figure out was it h17 or h19 that states what I think it states. If you just name the hypothesis by what it represents, that makes your life easier sometimes. Anyway, our goal is to prove that x equals 5. This shouldn't be very hard, but if you don't know the syntax, if you don't know what command does it, you'll be out of luck. Our goal is to prove exactly the same statement as one of the hypotheses. That goal, to solve this goal, the syntax is to write the word exact, then a space, and then the name of the hypothesis which matches the goal. Okay, so right here, I'm going to click, and what command shall I write? Sean. Exact space h, and then I hit enter, and we solved the level. Okay, that wasn't so hard. They're going to get harder. Okay, you've completed your first proof, your first Lean proof involving the real numbers. Remember, the exact tactic is used when you have exactly the same thing that you're trying to prove in the goal. Notice in the top right, your list of tactics, in the top right, your list of tactics now includes the tactic exact. And if you forget how it works, I forget how does exact work, I click on it, and it says exact solves a goal when one of the hypotheses is exactly the same as the goal. That's the syntax is exact and then space and then the name of the hypothesis. And you can X that out, and we'll move on to the next goal. Any questions so far? Satya.
If we're not storing the goal as like how this syntax better.
All of this is being stored under the hood, and we're just playing a video game.
Oh, we're not looking at Lean syntax, right?
We're not looking at Lean syntax. In fact, my hope is to never have you, well, that's not true. At some point, maybe we'll look at actual Lean syntax. But my hope is that this can all be done as a video game,
Okay.
where what's happening under the hood, ignore, and then you just have we're just trying to figure out how to solve these kinds of
So
questions.
is exact something that you came up with, or is that?
No, that's Lean syntax. I'm trying to, I will use only things that are in Lean. Well, that's not true either. Let's keep going. Yeah. We're going to learn how to play this video game. So everybody has learned one thing. We have one skill. If we have a hypothesis that says exactly the same thing as what the goal is trying to say, you just say exact in the name of the hypothesis. All right. Next. Here's a new goal. So we have two real numbers, x and y. Our goal is to show that x squared plus 2y is equal to x squared plus 2y. This also shouldn't be very difficult, but I can't say exact h because there's no h. There's no hypothesis to work with. So what do you do in that sense, in that setting? This isn't quite the same as our previous exercise. We don't have that. It's not exact something. There is no something. Instead, what we're going to use is the equal sign has a reflexive property. A is always equal to A, regardless of what A is. And the reflexive property of the equal sign in Lean is called RFL. Okay, so if you get to a situation where your goal is to prove that x is equal to x, and whatever, when the two things on both sides are literally identically the same, that will always be solved by appealing to the reflexive property of the equal sign. So what shall I type here? Brandon. RFL, yeah. And if we need more help, we can click on more help, write RFL. Okay, got it. RFL, enter. Whew, that wasn't so bad. All right. You've learned the REFL tactic. The key difference is if you have a hypothesis that matches exactly what the goal is, or REFL when you just need to, when the goal is itself is already the two things are equal to each other, when they're literally the same thing, exactly the same thing. Okay, now we have two tactics that have been unlocked, exact and REFL. Next. So far, so good? All right. Rewriting with equalities. Our objects are real numbers x and y. Our assumption, now I decided to call the assumption Bob, just to mess with you, is that x is equal to 2. And our goal is to prove that x plus y is equal to 2 plus y. Now x is equal to 2, so 2 plus y is equal to 2 plus y, so shouldn't REFL work?
Yes. Fall first.
These are not literally identically the same thing yet. Exactly right. So I can't say REFL. Can I say exact Bob? No, because Bob says x equals 2. That's not exactly the same thing as what the goal is. So we need some way of rewriting the fact that x is equal to 2 into the goal, and then we'll be able to solve it. So what's the tactic for that? It's called rewrite. The syntax, I didn't make this up. I'm sorry about these square brackets. They're there, and neither you nor I can do anything about them. The syntax is rewrite square bracket the name of the hypothesis. Okay. All right. So what should we do? Don't tell me. Tell me again. Jonathan. John.
You can rewrite open bracket Bob plus bracket.
Beautiful. Rewrite Bob. And watch what happens. We're not done. We're not done. So our previous goal state was here. We did rewrite Bob. This is our new goal state. Our goal state changed. It went from we had Bob that x equals 2, and our goal was x plus y is 2 plus y. Our new assumptions and objects didn't change, but the goal changed. The goal changed to 2 plus y is equal to 2 plus y. How can we solve that? Brandon.
No,
RFL, REFL. Okay, so we can chain these things together. So far, so good. So we've learned the rewrite tactic. Notice what happened after you wrote rewrite Bob. Okay, this is, if you're trying to play this game by yourself, I think we can move on. Any questions? So far, so good. Okay. Next, what do we have? Algebraic manipulation. Does anybody know what x plus y all cubed is? When you write it out, you know Pascal's formula, Pascal triangle, binomial theorem. So it comes out to this. That's not a surprise to anybody. So we have two real numbers, x and y. Our goal is to show that x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. That's a lot of arithmetic. You just, you gotta like do all these ring operations, multiply everything out. We don't want to be doing that by hand. I trust that you can do algebraic manipulations. So there's a tactic, a powerful tactic called ring normal form, ring underscore NF. And it will handle things like expanding products, collecting like terms, rearranging, using commutativity and associativity, and applying the distributive law. Okay, so if you have an algebraic identity that only involves addition, subtraction, multiplication, the ring tactic will often prove it automatically. Let's try it out. What should I type here? Ring NF, ring normal form. I hit enter, great. Pretty easy. Okay. I think this one is a good quiz. Let's do a quiz. So take out a piece of paper, put your name on it, and rip it off. Okay, write down the objects. So say put your name, make sure you have your name. The objects are X, Y, colon, bold R. You guys know how to write bold R's? You write it like this. One, two, and like that. That's a bold R for the real numbers. Okay, so those are your objects. Your goal is that there exists some real number C, so that x plus y to the fourth is equal to x to the fourth plus 4x cubed y plus c x squared y squared plus 4xy cubed plus y to the fourth. You don't yet know how to do this. I'm going to help you. I'm going to help you do this. I'm just giving you a chance to first write down what the goal is. Okay, so has everyone written objects, x, y, a real goal, and there exists, do you know this symbol? There exists backwards C, backwards E. This means there exists, so there's some number. I want to work out what this coefficient, what's the coefficient of x squared, y squared in the expansion of x plus y to the fourth? Does everyone know what value of C is supposed to go there? I hope so. So if your goal is to show that something exists, the question is, what value should we use? And the name of the tactic for that is use. So suppose you thought that 42 was the answer, you would write use space 42. You write use space 42, and the goal would be replaced by x plus y to the fourth is equal to x to the fourth plus 4y cubed y plus 42 x squared y squared plus 4xy cubed plus y to the fourth. We still won't be done. How would we finish it after that? Think about that, write it down. Okay, is anyone totally lost? Okay. So our goal is to show that there exists some number for which this identity holds. First, work out what you think that number is. Then your first answer should be use, let's say you think that number is 42, you would say use space 42. And on the next line, imagine what will happen when you put in use 42. Instead of saying there exists a C, we'll now get rid of the there exists and just replace every instance of C with 42. And now you have a new thing they have to prove. And you should already know how to prove that. Don't tell me. Just a second. Tell me. Akil.
What we're writing down, we have objects and goals. What should we put before like actual answer?
Command. You can put command. Sam.
We need to write the carets and asterisks.
No, just write it like as you're comfortable. Okay, does everybody have you solved your quiz? Okay, you're gonna grade them yourselves. So what did you get? What did you guys write first? Use 6. Okay, everybody figured out that 6 is the middle binomial coefficient. And now what? So now we have to prove this identity with a 6 in the middle. Ring and F. It's ring normal form operation, and the goal is done. Okay, so give yourself 1 if you got both of these, or a half if you got one but not the other, and a 0 if you just give yourself a 1. I don't care. Put a 1 on it and hand it forward, please. Okay, let's have Daniel collect them if that's okay. You're my point man here.
I have a question.
Yes.
So our REFL is looking at equality, right? But then ring NF is like simplifying it and then looking at equality?
Yes. Ring NF doesn't always complete the goal if there's more things to do. And we'll talk about that. Yeah. Yeah, I guess ring NF is a little too powerful. It doesn't just convert things into normal form. If it notices that both things are the same, it doesn't an extra REFL. right there. Perfect. Thank you. Okay, that wasn't so bad, Jeffrey.
So just as a question, like if you did ring NF like first.
Yes.
Then it wouldn't finish. Right?
Let's try. Ring NF. Ring NF says, here's what I got. In fact, that's a good way to cheat. You don't have to do the calculation yourself. You let the computer simplify things, but well, it's not that good actually, because now you have to sit there and point. Okay, I see the C there and I see the 6 there. So I see on both sides, you know, in what it kind of does it in some weird order.
Why do they have the coefficients afterwards?
That's what it has decided is the normal form. I agree, and you'll see that you don't want to use ring NF unless it's actually to close. Well, that's not true. There are also times when you want to use this ring tag. But the point is, if you just like, I don't want you to learn all the different ways that you have to learn that you have to solve algebra. I assume you can do algebra. You've done calculus, you can do algebra. Okay, so ring NF lets you simplify things. Right, and that so now if I use 6, yeah. So use 6 also closed the goal because it noticed that both sides were the same. That's funny. I didn't know that you could completely reverse the 2 operations, and you can. Of course, what I have in mind is that when there's a there exists, the way to make progress when your goal is there exists is to use the tactic use. Okay, so far so good. Next. So our growing toolkit includes exact, REFL, and rewrite for equality reasoning, ring NF for algebraic manipulation, and use for existential proofs. Next. Okay, our goal is to show that for all epsilon positive, epsilon plus 1 squared is equal to epsilon plus 1 squared. Okay, so that's 2 things that are equal on both, same things on both sides. We know what to do with that. REFL, right? The reflective property of the equal sign. RFL. No. It's not yet an equality. It's first a claim that for all epsilon positive, something happened. Okay, the fact the tactic failed, it's expected to have a binary relation, but it's not a binary relation, it's a for all. It's a universal quantifier first. Okay, so REFL doesn't work. We need something else. This is, okay, so let's read what we have here. In math, you often have to prove statements that are true for all values of some variable, like for all epsilon greater than 0, we have this. The condition that epsilon is positive is completely superfluous mathematically. It's here for a pedagogical reason. If you're thinking that REFL will do the trick, that's a good idea, but it won't because the goal is not yet an equality. Okay, we have to do something else first. In lean, as in mathematics, the way to make progress, if you're trying to prove a for all statement, if your goal is to show something's true for all values of epsilon positive, the first thing you should do is say, okay, so give me some arbitrary value of epsilon and give me the fact that epsilon is positive, and then I have to prove something. So introduce for me this value of epsilon and introduce for me the fact that it's positive. That's what you would say in mathematics. By the way, the way to write for all, just so you know, is backslash and the word for all, and then space, and you'll see this. Let me show you here. I'll do a backslash. You see the backslash? For all. And it turns into a for all. Okay, so you can type these things yourself. It's like LaTeX. And to write an epsilon, you write backslash e. Backslash e space gets us an epsilon. Okay, to prove a for all statement, you need to show that it's true for an arbitrary element. In English, what you would say, give me, or a more polite way to say give me is introduce. So introduce the variable epsilon and introduce the hypothesis, which we can call H, hypothesis on epsilon, H epsilon, that epsilon is positive. Okay, so the lean command for that is called intro. And you can name your dummy variable whatever you want. So we can write intro epsilon, that'll introduce the variable. So let's see, if I write, can I write intro epsilon? Should I write something else? Intro delta, great. Very perverse to use deltas in place of epsilons, but we got to do it. Introduce delta. Okay, so when I did our original goal was for all epsilon positive, epsilon plus 1 squared is equal to epsilon plus 1 squared. I said introduce delta. You see, this epsilon is a dummy variable. It could have been u or whatever. Look at what happened. Now we have a delta. We didn't have any objects before. Now we have a delta. And our goal is to show that if delta is positive, then delta plus 1 squared is equal to delta plus 1 squared. So REFL still won't work. We have to do another intro. Give me the delta, and give me the fact that delta is positive. What do you want to call the fact that delta is positive? H, sure. So I'll again intro H. Give me the fact that H is positive. And now I have a real number delta. I have the hypothesis that delta is positive. And now what I want to prove is that delta plus 1 squared is equal to delta plus 1 squared. We should do this by ring. Or REFL. REFL is a better way to do this. Okay, REFL is just the reflexive property. Boom. We're done. Okay. I realize I've thrown 1, 2, 3, 4, 5, 6 tactics at you so far, and I'm going to throw 2 more before the day's out. So this is why you're going to get practice with these things. You're not going to learn these things in one sitting. Okay, you're going to do them again and again, and you'll see how to do them. Okay. Any questions? Sam.
I didn't know what you wanted to see.
You mean here? So we have an implication. If delta is positive, then we have to prove something else. If delta is not positive, there's nothing to prove. So that's why intro, if you have P implies Q, intro will give you P as an assumption, and the goal will change to Q. Right? Does that make sense? Everybody's following that logic? Roger.
After you, what if you wanted to introduce another?
You mean create some other object out of thin air?
Yeah.
We will get there. We'll get there, but not yet. Yeah, I'll tell you the syntax for that. I don't want to throw too much syntax at you at once. There is a way to do it. Let me postpone the answer to your question. If that's okay. Okay, so far so good? Brendan?
I guess this is just, I mean, because you said, I guess, technically you could use ring instead of reflexive, but reflexive is just a kind of something or way to do it.
Yeah.
Say that? Okay.
Either one. Either one is a let's retry. Instead of REFL, let's try ring normal form. What that's going to do is multiply these out and see that they're the same on both sides and finish the goal. But don't bother multiplying it out. Right? I'm wasting some server flops or something. Don't tell me, John.
Yeah. Is there a reason why intro it's like it works on the for all as well as introducing a hypothesis, and is there a good reason for it?
The reason is that mathematically they're the same thing. Mathematically, this is asking for a function that takes a real number, and then it takes a proof that that real number is positive, and returns a proof that epsilon plus 1 squared is equal to epsilon plus 1 squared. So intro says, give me the first thing that you need in this function. Intro again says, give me the next thing that you need in this function, even though the things are different kinds of things. One is an object, one is an assumption. Actually, meta-mathematically, they're the same thing. I'm going to try to withhold, there's a lot of meta-math that's happening underneath this stuff that makes this possible, and I will try to stop myself from talking about it. Because it's not real analysis, and I want to teach you real analysis. But there's like, this is like Curry, yeah, it's type theory. Type theory is happening under the hood. Yeah, so let's not talk about it at all. Although it's very, very cool stuff. That's what makes this possible. So that's why the same word applies to 2 different kinds of things. They're not different kinds of things. They're the same kind of thing from a certain viewpoint.
Parameters.
Exactly. Okay. We have 5 minutes, right? Oh, no, we go till 30. Good. We're okay. We're okay. I thought we were going to run out of time. Any questions here? So far, so good? What's that? Is that clock's wrong? Anyway, I see it right there. It's 1:12. We have almost 20 minutes. Let's go. All right. Okay, let's do it. So check this problem out. Our objects, you guys are okay so far? I haven't burned your brains yet. I realize I'm throwing a lot at you. Is it going too slow?
Yes.
It's too easy. Okay, let's pick it up a pace. Our objects are a real number t, a function from real numbers to real numbers, an assumption that t is positive called t-pos, an assumption that for all positive x's, f of x is equal to x squared. That's our hypothesis. And our goal is to prove that f of t is equal to t squared. So logically, this should be trivial. We have real numbers t and f. We know that for every positive x, f of x is x squared. We know that t is positive. We're trying to prove that f of t is t squared. How do we do it? So when we had we know what to do if you have a there exists in the goal. If there exists in the goal, you make progress using use. I gave it away. If we have a for all in the goal, we make progress using intro. What if we have a for all in a hypothesis? How do we make progress when there's a for all in the hypothesis? So we know, I'm just going to explain this to you. I'm not going to read it to you. We know, again, this hypothesis is actually a function. It takes a real number x, it takes the proof that x is positive, and it returns f of x is equal to x squared. So if we specialize hf to not to x, but to t. So let's try that. So the suggestion is to say specialize hf at t. So what it does is it replaces hf, which says for any x whatsoever, as long as x is positive, yada, yada. It converts it into, not for any x, but when x is equal to t. If t is positive, then f of t is t squared. Okay, so it's really a function that takes an x, a proof that x is positive, and produces this. I've given it the x is t. Now it wants a proof that t is positive, and then it'll produce for you f of t equals t squared. What do? How do we provide a value into this function, John?
Did you specialize in HF?
Exactly right. It's again specialize for the same reason as before. It's specialize hf to t-pos, feed it into it, t-pos, and then you'll get this. So let's try that. Specialize hf t underscore pos. Why did I put an underscore? Now I have to fumble with my fingers. So now we've got 3 steps in this proof. The original goal was here. We specialized hf to t. Now we're specializing hf to t-pos. And look at what happened to hf. It's just that f of t is equal to t squared. Exact hf. Everybody follow? So far, so good? Let's do one more, and then we get the big boss. Okay. Now, our objects are a function f. The assumption that there exists some constant c for which f of c is equal to 2. There's some value for which f of c is equal to 2. And I want to know that my goal is to show that there exists some value of x for which f of x squared is equal to 4. Well, what do? If you want to show that there exists an x, you say use. So I'll say use c. So I'll write here, use c. What's c? We don't have c. C is not an object. Good guess. It's not intro because intro choose is yellow. Yes. So the fact, if you have, you know that if there's an exist in a goal, you write use. If you have an exist in an assumption, if you know if there's a hypothesis that such a c exists, you say, give me one of them, choose a particular value of c. There might be more than one. I don't know which one. Just choose one. I can't say anything other than it exists. Okay, so it's not going to be use c. It's choose, and then I have to give it the name. You want to call it c or, yeah, let's call it c. Why not? C and the hypothesis on C. So these things I'm making up. C and the hypothesis on C are words that I'm making up, names for that, right? But using, where am I supposed to get a C and the hypothesis on C? H, out of H. So H is actually a pair of things. It's a value of C together with a proof that f of C is equal to 2. And choose CHC using H is the way to get out that information. So when I write this command, I now have a value of C, and I have the hypothesis called HC that f of C is equal to 2. Does that make sense? Okay, our goal is there exists some x so that f of x is equal to 4, x squared is equal to 4, f of x squared is equal to 4. How many of you think you can finish it on your own? Okay, all right, so I'm not going too fast. So think about what you want to do now. Sam? Use C. There exists an x. When I want you to start seeing in your mind's eye what will happen when you write use C. When you write use C, what will happen? What will the goal turn into?
F of C squared equals 4.
F of C squared equals 4. What are you going to do with f of C squared equals 4?
H. Or no.
Sam?
Rewrite.
Rewrite brackets HC. We'll replace any instances of FC with 2. And now you'll get 2 squared equals 4. Refl's not going to do it, but ring NF will. It's just a ring operation. Okay, so I want you, just like a good chess player can see several moves ahead, your goal is to start seeing moves ahead without having the computer verify what the chess position is. Okay, so we'll use C. That makes the goal f of C squared is equal to 4. Where are we going to get the value of f of C? It's out of HC, so rewrite bracket HC. Now our goal is 2 squared equals 4, and we solve that with ring NF. Not REFL. Notice REFL doesn't work, but ring NF, ring normal form does. Okay, so big boss. And I think this is a good, I think we're perfectly on time. I'm going to give you 10 minutes to solve the big boss on your own. You have learned the exact, when the hypothesis exactly matches the goal. You've learned reflexivity, when you have two things on both sides being the same. You've learned the rewrite tactic, the ring tactic, the use tactic. Use is when there exists in the goal. Intro is when there's a for all in the goal. Specialize is when there's a for all in the hypothesis. Choose is when there's a exists in the hypothesis. Okay, and here's a little cheat sheet. Whether it's in the goal or the hypothesis, whether it's a universal or existential quantifier, if it's in the goal, you use. If it's in the hypothesis, you choose a value. If it's in the goal and the goal is for all values, use intro. If it's in a hypothesis, you can specialize it. Okay, here's your big boss. And we're going to do it the extra challenging way, at least for a few minutes. So, what's the problem? You have a function f. You have an existential hypothesis that there exists some value of a for which f of a is equal to 3. You have a universal hypothesis that for all values of x positive, f of x plus 1 is equal to f of x plus 9. Your goal is to show that there exists some value b, so that for all positive y, f of y plus 1 squared is equal to f of y plus f of b squared, all squared. You have all the tools necessary to try to solve this problem. Take 7 minutes and see if you can solve it. And then in the last minute, we'll come together. You can work with people around you, talk to one another, argue, debate. And let's see if we can solve this. So this is the challenge. We're doing the extra challenge. Why would you want to play this thing blind? You write the assumptions down on a piece of paper, close the computer, solve it by hand, keeping track in your mind of what the game board is doing after each command. And only once you've worked out the whole solution, open up the computer and see if Lean says, yes, it's right. Why would this be a good thing to do? I hope that your goal in taking this course is to strengthen your real analysis brain muscles. So in the end, you should be really good at solving real analysis problems on paper. You don't have to, where you don't have Lean showing you the goal state after every move. More broadly, the purpose of learning to solve real analysis problems is learning to think clearly, precisely, strengthening your ability to work with pen and paper, or just mentally, directly transfers to any context where you're wrestling with complicated ideas. Again, I said this already, a large language model can solve these things. So when you're doing your homework problems, you can put them into an LLM. That's like going to the gym, setting 200 pounds on the bench press, bringing over a forklift, and having the forklift lift it 30 times and saying, yay, I did it. You absolutely use a forklift when you're trying to build something or move something heavy. But if the goal of the activity is the exercise, then you don't use the forklift, you do it bare hands, right? Meet your neighbor, say hello, talk to them. Okay, so Roger, this is really good. When you're doing your homework, you don't have to rewrite the goal every single time. You can just say use 6 ring N. That's for everyone.
Could you scroll back up to the?
Sure. What do you want to see? The cheat sheet. Here's all of them. Exact, REFL, rewrite, ring, use, intro, specialize, choose. Here's the cheat sheet. Yeah, if you have 2 things for intro, you can either intro A, next line, intro B, or intro A space B.
There's Y, there's Y greater. So that first bit, right, one for the object Y. Exactly.
Expression.
Does everyone understand how to do it without worrying about what the lean command is?
Yeah.
Does everyone work through why it's true before you try to write it formally? What's the syntax for specialize? It's specialize the name of the hypothesis and then what you want to specialize it to. Should we do it together? I don't want to run out of time. Or do you want more time to think about it? Let's do it together. Let's come back. Because I think, did anybody think they got it? Okay. Jeffrey, how did you, what were you thinking about when you started it off?
I guess first to deal with the existential, I just want to pick a value. So
Yeah, what value of B are we gonna want to use in the end
it's just the same
as
like H existential.
A, exactly. So we got to get that, we have to choose that A before we can make progress. So what was your first line?
But choose a H universal using H existential.
So it's choose A is the name of the thing,
Yeah.
and then you give it your own name, like HA, for the fact
Okay.
that it comes with. And then it's using H existential. And if you forgot, you click on choose. Well, you can't click on choose. Oh, I need to give you more. Yeah, it's right here. Choose value, hypothesis on value, and then using. Why is it jumping around? Using, then the name. Okay, so using H existential. Okay, so we've got a value for A, and we've got the fact that f of A is equal to 3. Now what? Daniel? Use A. That's the value that we want for B. Okay, use A. All right. For all y positive,
Or Y.
intro y, and you can do another intro hy, or you can do both of them at the same time, intro y, hy. Okay, so now we have real numbers A and Y. We have the hypothesis that f of A is 3. We have the hypothesis that y is positive. Sam?
Specialize H universal Y H Y.
Beautiful. Specialize H universal to not for any value of x, but for x equals y, and then y, how come, I can't say y, and then how come x is positive, or x has now been replaced by y, how come y is positive? Because of hy. And now it's stuck in for x equal to y, and for x positive, it's stuck in y positive. And now we know that H universal has become the fact that f of y plus 1 is equal to y plus 9. Now what? Sam?
Rewrite.
Rewrite H universal. That's going to replace f of y plus 1 with f of y plus 9. It's still not done, because we're trying to say that f of y plus 9 squared is equal to f of y plus f of a squared all squared. Daniel?
Right, H A.
Rewrite HA, because HA will replace f of a by 3. And now we have f of y plus 9 all squared is equal to f of y plus 3 squared all squared. It's not REFL, but it is ring. That's the big boss.